Space Launch System, SLS. The Space Launch System, SLS, is an American super heavy-lift, SHLLV, expendable launch vehicle, ELV, used by the National Aeronautics and Space Administration, NASA. As the primary launch vehicle of the Artemis Moon landing program, SLS is designed to launch the crewed Orion Multi-Purpose Crew Vehicle or Orion MPCV, spacecraft on a trans-lunar trajectory, TLT. SLS first launched on November 16, 2022 for the uncrewed Artemis I mission, formerly Exploration Mission 1, EM1. Development of SLS began in 2011 as a replacement for the retiring Space Shuttle and the cancelled Ares I, originally known as the Crew Launch Vehicle or CLV, and Ares V, formerly known as the Cargo Launch Vehicle or CLV, launch vehicles. The Space Launch System was built using a combination of shuttle components, including Space Shuttle Solid Rocket Boosters, SRBs, and RS-25 engines, also known as the Space Shuttle Main Engines, SSMEs, and new technology such as the Space Launch System Core Stage, or simply Core Stage. The project has seen mismanagement, budget overruns, and delays. The first launch, required by Congress to take place by 2016, occurred nearly 6 years later. All Space Launch System flights are to be launched from Launch Complex 39B, LC-39B, at the John F. Kennedy Space Center, KSC, in Florida. The first 3 SLS flights are expected to use the Block 1 configuration, comprising a core stage, extended Space Shuttle boosters developed for Ares I, and the Interim Cryogenic Propulsion Stage, ICPS, upper stage. The improved Block 1B configuration, with the purpose-built Exploration Upper Stage, EUS, is to be introduced on the 4th flight, and a further improved Block 2 configuration with new solid rocket boosters is planned for the 9th flight. The SLS is a Space Shuttle-derived launch vehicle, SDV. The rocket's first stage is powered by 1 central core stage and 2 outboard solid rocket boosters. All SLS blocks share a common core stage design but differ in their upper stages and boosters. Together with the solid rocket boosters, the core stage is responsible for propelling the upper stage and payload out of the atmosphere to near orbital velocity. It contains the liquid hydrogen and liquid oxygen tanks for the ascent phase, the forward and aft solid rocket booster attach points, avionics, and the main propulsion system, MPS. An assembly of the 4 RS-25D, E engines, associated plumbing and hydraulic gimbal actuators, and equipment for autogenous pressurization of the vehicle's tanks. The core stage provides approximately 25% of the vehicle's thrust at liftoff, the rest coming from the solid rocket boosters. The stage measures 65 meters, 213 feet, long by 8.4 meters, 28 feet, in diameter and is visually similar to the Space Shuttle External Tank, AT. It is made mostly of 2219 aluminum alloy, and contains numerous improvements to manufacturing processes, including friction stir welding, FSW, for the barrel sections, and integrated milling for the stringers. The first 4 flights will each use and expend 4 of the remaining 16 RS-25D engines previously flown on Space Shuttle missions. Aerojet Rocketdyne refits these engines with modernized engine controllers, higher throttle limits, as well as insulation for the high temperatures the engine section will experience due to their position adjacent to the solid rocket boosters. Later flights will switch to an RS-25 variant optimized for expended use, the RS-25E, which will lower per-engine costs by over 30%. The thrust of each RS-25D engine has been increased from 2,188 kilonewtons, 492,000 pounds force, as on the Space Shuttle, to 2,281 kilonewtons, 513,000 pounds force, on the 16 modernized engines. The RS-25E will further increase per-engine thrust to 2,321 kilonewtons, 522,000 pounds force. The first test firing of a RS-25E took place in June 2025 and was declared a success. Blocks 1 and 1B of the SLS will use 2 5-segment solid rocket boosters. They use casing segments that were flown on shuttle missions as parts of the 4-segment Space Shuttle Solid Rocket Boosters, SRBs. They possess an additional center segment, new avionics, and lighter insulation, but lack a parachute recovery system, as they will not be recovered after launch. The propellants for the solid rocket boosters are aluminum powder, AL, which is very reactive, and ammonium perchlorate, a powerful oxidizer. They are held together by a binder, polybutadiene acrylonitrile, PBAN. The mixture has the consistency of a rubber eraser and is packed into each segment. The 5-segment solid rocket boosters provide approximately 25% more total impulse than the shuttle's solid rocket boosters. The stock of SLS Block 1 to Block 1B boosters is limited by the number of casings left over from the shuttle program, which allows for 8 flights of the SLS. On March 2, 2019, the Booster Obsolescence and Life Extension (BOL) program was announced, with the goal of developing new solid rocket boosters for SLS Block 2. These boosters will be built by Northrop Grumman Space Systems, and will be derived from the composite casing solid rocket boosters then in development for the cancelled Omega Medium Lift (MLV) to Heavy Lift Launch Vehicle (HLV), and are projected to increase Block 2's payload to 130 metric tons, 290,000 pounds, to low Earth orbit (LEO), and at least 46 metric tons, 101,000 pounds, to trans-lunar injection (TLI). As of 2025, the BOL program is under development, with first firing of a prototype taking place in June of that year, which experienced a nozzle failure, exploding about 2 minutes into the burn. The Interim Cryogenic Propulsion Stage, ICPS, is a temporary upper stage for Block 1 versions of SLS, built by United Launch Alliance, ULA, a joint venture of Boeing and Lockheed Martin. The ICPS is essentially an off-the-shelf Delta Cryogenic Second Stage, DCSS, with minimal modifications for SLS integration. The ICPS is intended as a temporary solution and slated to be replaced on the Block 1B version of the SLS by the Next Generation Exploration Upper Stage, EUS, under design by Boeing. The ICPS used on the Artemis I mission was powered by a single RL-10B2 engine, while the ICPS for Artemis II and Artemis III missions will use the RL-10C2 engine variant. SLS Block 1 is intended to be capable of lifting 95 metric tons, 209,000 pounds, to low Earth orbit, LEO, in this configuration, including the weight of the ICPS as part of the payload. At the time of SLS core stage separation, Artemis I was traveling on an initial 1,806 by 30 kilometers, 1,122 by 19 miles, transatmospheric orbital, TAO, trajectory. This trajectory ensured safe disposal of the core stage. ICPS then performed orbital insertion and a subsequent trans-lunar injection burn to send Orion towards the Moon. The ICPS will be human-rated for the crewed Artemis II and III flights. The SLS Block 1 has a conical frustum-shaped interstage called the Launch Vehicle Stage Adapter, LVSA, between the core stage and the ICPS. It consists of 16 aluminum-lithium, ALLI, panels made of 2,195 aluminum alloy. Teledyne Brown Engineering, division of Teledyne Technologies Incorporated, is its builder. The first one cost $60 million, and the next two cost $85 million together. The Exploration Upper Stage, EUS, is planned to first fly on Artemis IV. The EUS will complete the SLS ascent phase and then reignite to send its payload to destinations beyond LEO. It is expected to be used by Block 1B and Block 2. The EUS shares the core stage diameter of 8.4 meters, 28 feet, and will be powered by 4 RL-10C3 engines. It will eventually be upgraded to use 4 improved RL-10CX engines. As of March 2022, Boeing is developing a new composite-based fuel tank for the EUS that would increase Block 1B's overall payload mass capacity to trans-lunar injection, TLA, by 40%. The improved upper stage was originally named the Dual-Use Upper Stage, DUSE, but was later renamed the Exploration Upper Stage, EUS. During the joint Senate-NASA presentation in September 2011, it was stated that the SLS rocket program had a projected development cost of $18 billion through 2017, with $10 billion for the SLS rocket, $6 billion for the Orion spacecraft, and $2 billion for upgrades to the launch pad and other facilities at Kennedy Space Center. These costs and schedules were considered optimistic in an independent 2011 cost assessment report by Booz Allen Hamilton Incorporated, division of Booz Allen Hamilton Holding Corporation, informally Booz Allen, for NASA. An internal 2011 NASA document estimated the cost of the SLS program through 2025 to total at least $41 billion for 495 metric tons, 209,000 pounds, launches, 1 uncrewed and 3 crewed, with the 130 metric tons, 290,000 pounds, version ready no earlier than 2030. The Human Exploration Framework Team, HEFT, estimated unit costs for Block 0 at $1.6 billion and Block 1 at $1.86 billion in 2010. However, since these estimates were made, the Block 0 SLS launch vehicle was dropped in late 2011, and the design was not completed. In September 2012, an SLS deputy project manager stated that $500 million is a reasonable target average cost per flight for the SLS program. In 2013, the Space Review estimated the cost per launch at $5 billion, depending on the rate of launches. NASA announced in 2013 that the European Space Agency, ʻnæsə, will build the Orion Service Module or the European Service Module, ESM. In August 2014, as the SLS program passed its Key Decision Point C, KDPC, review and was deemed ready to enter full development, costs from February 2014 until its planned launch in September 2018 were estimated at $7.021 billion. However, ground systems modifications and construction would require an additional $1.8 billion over the same time. In October 2018, NASA's Office of Inspector General, NASA OIG or OIG, reported that the Boeing core stage contract had made up 40% of the $11.9 billion spent on the SLS as of August 2018. By 2021, development of the core stage was expected to have cost $8.9 billion, twice the initially planned amount. In December 2018, NASA estimated that yearly budgets for the SLS will range from $2.1 billion to $2.3 billion between 2019 and 2023. In March 2019, the Trump administration released its fiscal year 2020 budget request for NASA, which notably proposed dropped funding for the Block 1B and Block 2 variants of SLS rocket. Congressional action ultimately included the funding in the past budget. One lunar gateway component that had been previously planned for the SLS Block 1B is expected to fly on the SpaceX Falcon Heavy Super Heavylift Launch Vehicle, SHLLV. On May 1, 2020, NASA awarded a contract extension to Aerojet Rocketdyne to manufacture 18 additional RS-25 engines with associated services for $1.79 billion, bringing the total RS-25 contract value to almost $3.5 billion. NASA has spent $29.0 billion on SLS development from 2011 through 2024, in nominal dollars. This is equivalent to $35.4 billion in 2025 dollars using the NASA New START inflation indices. In 2025, the enacted NASA budget for exploration, which includes SLS, is approximately the same again as 2024. In January 2024, NASA announced plans for a first crewed flight of the Orion spacecraft on the SLS, the Artemis II mission, no earlier than February 2026. Excluded from the SLS rocket cost above are the costs to assemble, integrate, prepare and launch the SLS and its payloads, funded separately in the NASA Exploration Ground Systems, EGS, currently at about $600 million per year, and anticipated to stay there through at least the first 4 launches of SLS. Also excluded are payloads that launch on the SLS, such as the Orion Crew Capsule, the predecessor programs that contributed to the development of the SLS rocket, such as the Ares 5 Cargo Launch Vehicle, SHLLV, project, funded from 2008 to 2010 for a total of $70 million, and the Ares 1 Crew Launch Vehicle, CLV, funded from 2006 to 2010 for a total of $4.8 billion in development, including the 5-segment solid rocket boosters used on the SLS. Despite calls from the Trump administration to terminate the SLS program after Artemis III mission, the 2025 One Big Beautiful Bill Act, OBBBA, or the Big Beautiful Bill, PL 1/1921, included $4.1 billion to fund SLS rockets for the Artemis IV and Artemis V missions, with mandated minimum spending of $1.025 billion per year from fiscal year 2026 through 2029. However, as a compromise, lawmakers have suggested eliminating the Exploration Upper Stage, EUS, and directed NASA to evaluate alternatives such as the Centaur 5 or the GS-2 upper stage used on the New Glenn rocket. The SLS was created by an act of the U.S. Congress in the NASA Authorization Act of 2010, Public Law 111-267, in which NASA was directed to create a system for launching payloads and crew into space that would replace the capabilities lost with the retirement of the Space Shuttle. The Act set out certain goals, such as, being able to lift 70 to 100 metric tons, 150,000 to 220,000 pounds, into low Earth orbit with evolvability to 130 metric tons, 290,000 pounds. A target date of December 31, 2016 for the system to be fully operational, and a directive to use, to the extent practicable, existing components, hardware, and workforce from the Space Shuttle and from Ares 1 human-rated orbital launch vehicle. On September 14, 2011, NASA announced their plan to meet these requirements, the design for the SLS, with the Orion spacecraft as payload. The SLS has considered several future development routes of potential launch configurations, with the planned evolution of the blocks of the rocket having been modified many times. Many options, all of which just needed to meet the congressionally mandated payload minimums, were considered, including a SLS Block 0 variant with 3 main engines, a variant with 5 main engines, a Block 1A variant with upgraded boosters instead of the improved second stage, and a Block 2 variant with 5 main engines plus the Earth Departure Stage, EDS, with up to 3 J2X engines. In the initial announcement of the design of the SLS, NASA also announced an advanced booster competition to select which boosters would be used on Block 2 of the SLS. Several companies proposed boosters for this competition, all of which were indicated as viable. Aerojet Company and Teledyne Technologies Inc. proposed 3 booster engines each with dual combustion chambers. Alliant Techsystems Inc., ATK, proposed a modified solid rocket booster with lighter casing, more energetic propellant, and 4 segments instead of 5, and Pratt & Whitney Rocketdyne, PWR, and Dynetics proposed a liquid-fueled booster named Pyrrhos. However, this competition was planned for a development plan in which Block 1A would be followed by Block 2A, with upgraded boosters. NASA cancelled SLS Block 1A and the planned competition in April 2014, in favor of simply remaining with the Ares 1's 5-segment solid rocket boosters, themselves modified from the Space Shuttle's solid rocket boosters, until at least the late 2020s. The overly powerful advanced booster would have resulted in unsuitably high acceleration, and would need modifications to launch Complex 39B, LC-39B, its flame trench, and mobile launcher. On July 31, 2013, the SLS passed Preliminary Design Review, PDR. The review included not only the rocket and boosters but also ground support and logistical arrangements. On August 7, 2014, the SLS Block 1 passed a milestone known as Key Decision Point C and entered full-scale development, with an estimated launch date of November 2018. In 2013, NASA and Boeing analyzed the performance of several Exploration Upper Stage, EUS, engine options. The analysis was based on a second-stage usable propellant load of 105 metric tons, 231,485 pounds, and compared stages with 4 RL-10 engines, 2 Mark 60 engines, or 1 J2X engine. In 2014, NASA also considered using the European restartable, cryogenic, liquid propellant rocket engine Vinci instead of the RL-10 engine, which offered about the same specific impulse but with 64% greater thrust, which would allow for the same performance at a lower cost. In 2018, Blue Origin Enterprises, Limited Partnership, LP, submitted a proposal to replace the EUS with a cheaper alternative to be designed and fabricated by the company, but it was rejected by NASA in November 2019 on multiple grounds. These included lower performance compared to the existing EUS design, incompatibility of the proposal with the height of the door of the Vehicle Assembly Building, originally the Vertical Assembly Building, or VAB, being only 120 meters, 390 feet. An unacceptable acceleration of Orion components such as its solar panels due to the higher thrust of the engines being used for the fuel tank. From 2009 to 2011, 3 full-duration static fire tests of 5-segment solid rocket boosters were conducted under the Constellation program, including tests at low and high core temperatures, to validate performance at extreme temperatures. The 5-segment solid rocket booster would be carried over to SLS. Northrop Grumman Innovation Systems, former Orbital ATK Incorporated, has completed full-duration static fire tests of the 5-segment solid rocket boosters. Qualification Motor 1, QM1, was tested on March 10, 2015. Qualification Motor 2, QM2, was successfully tested on June 28, 2016. On February 7, 2025, Boeing, the primary contractor for the SLS, informed its employees working on the rocket program that they may face layoffs when the company's contract expires in March. The announcement coincided with the anticipated release of the presidential budget, suggesting the Trump administration might propose canceling the SLS program. On May 2, 2025, the Trump administration released its fiscal year 2026 budget proposal for NASA, which calls for terminating the SLS rocket and Orion spacecraft programs after Artemis III. The budget proposal described the SLS as grossly expensive, noting that it costs $4 billion per launch and has exceeded its budget by 140%. The U.S. budget allocates funding for a program to transition to more cost-effective commercial systems, a move projected to save NASA $879 million. The 2025 One Big Beautiful Bill Act included funding for SLS rockets for the Artemis IV and Artemis V missions, but a clause directed NASA to evaluate alternatives to the EUS. NASA has been reluctant to provide an official per-flight cost estimate for the SLS. However, independent agencies, such as the White House Office of Management and Budget, OMB, and the NASA Office of Inspector General, have offered their own estimates. A White House Office of Management and Budget letter to the United States Senate Committee on Appropriations, informally known as the Senate Appropriations Committee, in October 2019 estimated that SLS's total cost to the taxpayer was estimated at over $2 billion per launch. When questioned by a journalist, a NASA spokesperson did not deny this per-flight cost estimate. The NASA Office of Inspector General has conducted several audits of the SLS program. A November 2021 report estimated that, at least for the first 4 launches of Artemis program, the per-launch production and operating costs would be $2.2 billion for SLS, plus $568 million for exploration ground systems. Additionally, the payload would cost $1 billion for Orion spacecraft and $300 million for the European Service Module. An October 2023 report found that recurring production costs for SLS, excluding development and integration costs, are estimated to be at least $2.5 billion per launch. In 2025, Sean Duffy, then the acting NASA administrator, said that Artemis I, Artemis II, and Artemis III missions are all $4 billion a launch. NASA has said that it is working with Boeing to bring down the cost of SLS launches and that a higher launch frequency could potentially lead to economies of scale, and would allow fixed costs to be spread out over more launches. However, the NASA Office of Inspector General has called NASA's cost savings goals highly unrealistic, and other potential government customers have made it clear they have no interest in using SLS. As of 2020, 3 SLS versions are planned: Block 1, Block 1B, and Block 2. Each will use the same core stage with its 4 main engines, but Block 1B will feature the exploration upper stage, and Block 2 will combine the EUS with upgraded boosters. The ICPS for Artemis I mission was delivered by ULA to NASA about July 2017 and was housed at Kennedy Space Center as of November 2018. In mid-November 2014, construction of the first core stage hardware began using a new friction stir welding system in the South Vertical Assembly Building, or Vertical Assembly Center, Weld High Bay, at NASA's Michoud Assembly Facility, MAF. Between 2015 and 2017, NASA test-fired RS-25 engines in preparation for use on SLS. The core stage for the first SLS, built at Michoud Assembly Facility by Boeing, had all 4 engines attached in November 2019, and it was declared finished by NASA in December 2019. The first core stage left Michoud Assembly Facility for comprehensive testing at the John C. Stennis Space Center, SSC, in January 2020. The static firing test program at Stennis Space Center, known as the Green Run, operated all the core stage systems simultaneously for the first time. Test 7, of 8. The wet dress rehearsal, was carried out in December 2020 and the fire, Test 8, took place on January 16, 2021, but shut down earlier than expected, about 67 seconds in total rather than the desired 8 minutes. The reason for the early shutdown was later reported to be because of conservative test commit criteria on the thrust vector control system, specific only for ground testing and not for flight. If this scenario occurred during a flight, the rocket would have continued to fly normally. There was no sign of damage to the core stage or the engines, contrary to initial concerns. The second fire test was completed on March 18, 2021, with all 4 engines igniting, throttling down as expected to simulate in-flight conditions, and gimbaling profiles. The core stage was shipped to Kennedy Space Center to be mated with the rest of the rocket for Artemis I. It left Stennis on April 24 and arrived at Kennedy Space Center on April 27. It was refurbished there in preparation for stacking. On June 12, 2021, NASA announced the assembly of the first SLS rocket was completed at the Kennedy Space Center. The assembled SLS was used for the uncrewed Artemis I mission in 2022. The first SLS, for Artemis I, launched an Orion spacecraft into a lunar orbit on a test flight in fall 2022, and NASA and Boeing are constructing the next 3 rockets for Artemis II, Artemis III, and Artemis IV. Boeing stated in July 2021 that while the COVID-19 pandemic had affected their suppliers and schedules, such as delaying parts needed for hydraulics, they would still be able to provide the Artemis II SLS core stage per NASA's schedule, with months to spare. The spray-on foam insulation process for Artemis II was automated for most sections of the core stage, saving 12 days in the schedule. The Artemis II forward skirt, the foremost component of the core stage, was affixed on the liquid oxygen tank in late May 2021. By September 25, 2023 the core stage was functionally complete, as all sections were assembled and the 4 RS-25 engines had been installed. The complete core stage was set to ship to NASA in late fall 2023, 8 months later than was predicted originally. The complete core stage was delivered in July 2024. For Artemis III, assembly of elements of the thrust structure began at Michoud Assembly Facility in early 2021. By August 2025, the thrust structure was completed and moved to storage in the Vehicle Assembly Building at Kennedy, to await the rest of the stage's arrival in mid-2026. The liquid hydrogen tank for Artemis III was originally planned to be the Artemis I tank, but it was set aside as the welds were found to be faulty. Repair techniques were developed, and the tank re-entered production and will be proof-tested for strength, for use on Artemis III. As of July 2021, Boeing is also preparing to begin construction of the exploration upper stage, which is planned to be used on Artemis IV. Originally planned for late 2016, the uncrewed first flight of SLS slipped more than 26 times in almost 6 years. As of earlier that month, the first launch was originally scheduled for 8:30 a.m. Eastern Daylight Time, August 29, 2022. It was postponed to 2:17 p.m. Eastern Daylight Time, 18:17 Coordinated Universal Time, September 3, 2022, after the launch director called a scrub due to a temperature sensor falsely indicating that an RS-25 engine's hydrogen bleed intake was too warm. The September 3, 2022, attempt was then scrubbed due to a hydrogen leak in the tail service mast quick disconnect arm, which was fixed. The next launch option was at first a period in late October 2022 and then a launch in mid-November 2022, due to unfavorable weather during Hurricane Ian. It launched on November 16, 2022. NASA originally limited the amount of time the solid rocket boosters can remain stacked to, about a year, from the time two segments are joined. The first and second segments of the Artemis I boosters were joined on January 7, 2021. NASA could choose to extend the time limit based on an engineering review. On September 29, 2021, Northrop Grumman indicated that the limit could be extended to 18 months for Artemis I, based on an analysis of the data collected when the boosters were being stacked. An analysis weeks before the actual launch date later extended that to December 2022 for the boosters of Artemis I, almost 2 years after stacking. In late 2015, the SLS program was stated to have a 70% confidence level for the first Orion flight that carries crew, the second SLS flight overall, to happen by 2023. As of November 2021, NASA delayed Artemis II from 2023 to May 2024. In March 2023, NASA announced they had delayed Artemis II to November 2024. In January 2024 the mission was further delayed to September 2025, and in December 2024 it was announced that the launch was pushed back to February 2026.